This is the demonstration of the Hanoi Tower. So the game of Hanoi Tower is to move a set of disks from one place to another place. And during the time, we cannot violate the order, the disk with the smallest on top, the biggest at the bottom, and with the increased size ordered during the transfer. So if there's one disk, we can just move it. So that's straightforward. If there are two disks, and we need to move the smaller one to a spare site, and then move the biggest one to the target, and then move the smaller one to the target. So if there are three, then we need to move the smaller one to the target, middle one to the spare, smaller one to the spare, the largest one to the target, smaller one, and then the middle one, and then finally the smaller one. So this is the classical example of recursion. And the basic idea is we know how to solve one disk and two disks, but we want to partition the larger problem into smaller problems. So we can think there's one disk, and then the rest of it we consider as a smaller problem. So here's the implementation. So we know how to move one disk. That's the base solution. With one disk, we just move from the front position to the target position. Right, so 2 is our target position here. That's the recursive definition of the Hanoi Tower. But what happened to the smaller problem? It's a 3 disk. We know how to solve the second one, 2 disk problem. Right, so when the 2 disk problem, we move the smaller problem to a spare and the largest one to the target. And then, so this is just a 3-step. In this case, we first move the smaller problem to the spare. That's move the smaller problem to the spare, and move the remaining, that's the last disk, to the target. And finally, we move that smaller problem from spare to the target. In this case, that's the n-1 situation. We just move that. So this and this code basically says if we have one disk, we move from the front to the target. If there are more than one disk, I'm going to move the smaller one problem from the front to the spare, and then the remaining one disk from that front to the target, and then we move that smaller problem from the spare to the target. That's the so let's and in this case I also print out the steps. So with one disk, well, it's just one. With 2 disks, we have 3 steps. Let's verify that. So we have 2 disks. First one from front to spare, and then second step from front to target, and the third step from spare to target. Oops, sorry. There. And then if we have 3 steps, now we have 7 moves. So let's see. First, front to target. That's the front to target. Second, front to spare. Third, target to spare. Fourth, front to target. 5, spare to front. 6, spare to target. 7, front to target. 7 moves. So, and you can actually try this for the number 4, and that will be 15 moves. And in this case, if you follow it, hopefully it's working. Let's say 1 from front to spare, second front to target, third spare to target, fourth front to spare, fifth target to front, sixth target to spare, 7 front to spare, 8 front to target. So now we have moved the largest disk. Very good. 9 spare to target, 10 spare to front, 11 target to front, 12 spare to target, 13 front to spare, 14 front to target, finally spare to target, 15 move.